there's no specific proof, we are going to conclude this experiment they have conducted. This A is going to be the amplifier without feedback, and B is going to be the amplifier with feedback. So in A, I am not giving any feedback. It is an open loop amplifier, and see here the gain is going to be, variation in gain is large. It is very steep. The variation is very large in the case of A, but when you apply negative feedback to the amplifier as in case A, you are going to see that the linearity is going to be preserved. Okay, so the linearity is going to be completely preserved, and the graph is going to be having a very minor variation. So it is almost becoming linear. So even though you have a break here, which will make it piecewise linear, overall the graph looks almost a straight line, and then it is getting saturated. Okay, so A is going to be the amplifier without feedback, and B is going to be the amplifier when I'm going to apply negative feedback with beta value 0.01. So we can clearly see from the experiment that B is more linear compared to A, and B represents the negative feedback applied to the amplifier, and A represents the amplifier without the negative feedback. So the slope of the greatest, the first case, the feedback overall gain of the amplifier with feedback is given by AF is equal to 1000 by 1 plus 1000 into 0.01. 1000 is the maximum gain. So you get 90.09. And for the second amplifier, the maximum gain is 100 because of applying negative feedback. So 100 by 1 plus 100 into 0.01. So the variation is 50. See, compare 1090. It is very far. Compare 150. They are very close. So what you can say, the variation in slope is very, very minimum. Or I can say the linearity here is very less because the values are far apart, but the linearity here is very, very large because the values are very close. Very close means you can approximate that by a straight line. So the order of magnitude of change in slope has been considerably reduced when you compare A and B. So from A, the slope is very steep, and B, the slope is relatively, it's not that steep. It is looking like a straight line. So it is linear. Okay, so but again, this reduction in distortion is achieved at the expense of voltage gain. So definitely distortion will be reduced, noise will be reduced, all good things will happen, but your voltage gain will also be reduced. That is the only negative point about your negative feedback. So negative feedback will reduce your voltage gain at the expense of all these good things. Okay. So you can, if you feel that your gain is getting reduced, then before adding feedback, you can amplify the signal using an amplifier called as preamplifier. Okay, please understand that all properties of negative feedback are under the assumption that my gain is going to reduce. So if you're not interested in the reduction in gain, then you have to amplify your signal before you pass it to the feedback network. So in the previous case, we have seen the noise is reduced, but again, voltage gain is also reduced. Now we see distortion is reduced, but again, the voltage gain is also reduced. If you don't want to reduce the voltage gain of an amplifier, just you want to reduce noise and distortion, then before applying feedback, you do pre-amplification. So before you apply negative feedback, pass the signal through a pre-amplifier, and this pre-amplifier will amplify the signal in such a way that even if you apply negative feedback, the gain will not be reducing so much. So this pre-amplifier should not present. Again, this pre-amplifier should be linear. If this pre-amplifier is also non-linear, then it will also add distortion. That is not good. So whatever amplifier you choose for pre-amplification, it should not add distortion to the signal. It should be a highly linear amplifier. Then only the purpose of reducing non-linear distortion will be effectively possible when you are going to apply negative feedback.